We're now starting Unit 3, which starts with solutions, which includes both chapters 4 and 13. So chapter 4 should hopefully be a review from other science classes you've taken, and it's going to just be the basics of aqueous solutions. There is way more in chapter 4, but I'm just going to focus on the select amount of information that I want you to know and review. So we're going to first define solutions. So solutions are defined as homogeneous mixtures of two or more pure substances. And so we think of a solution as something that, if I have sugar and I'm going to dissolve it into water, right? Then we think of the water and I have to dissolve something. But this is not the case for the most broad definition of solution. So, for example, we have air, right? Let's say this is a sample of air. Air is made up of about 78% nitrogen, 21% oxygen, and then about 1% of miscellaneous things, other elements. And so this would be an example of a solution where we have pure substances, right? Nitrogen, oxygen, and these other compounds and elements, but there's no dissolving is how we would normally consider it. So the way we're going to dissolve the solvent is the substance that has is present in the greatest abundance. So the majority thing. Normally we think of the solvent as water because usually water has the most amount. The other substances are called the solutes, so the minority. So here I have nitrogen being my solvent because it's present in the greatest abundance, and then oxygens and other gases such as carbon dioxide and argon and such are the solutes. So when water is a solvent, we call that solution an aqueous solution, and we often denote it as the phase as being AQ. We can have substances dissolve in water in a couple of different ways. So if I have an ionic compound, then the water molecules are going to come and attract to the ions and pull it apart, and we talked about that when we discussed ion-dipole interactions. And so they are going to break into ions when that happens. When we have molecular compounds such as sugar, water is going to interact with them and attract to them, but they're not going to break apart. They're going to stay intact. So I'd have a full sugar molecule surrounded by water. And this specifically happens with polar molecular substances like sugar because they attract water to them, or water gets attracted to them. And so this causes them to break apart from one another. So when we create solutions, we can also classify them as electrolytes or non-electrolytes in that solution. So to define an electrolyte is a substance that breaks completely into ions when it dissolves in water. So it fully dissolves. So this could be, I have sodium chloride, it's a solid. When I put it into water, right, with water in there, it completely breaks apart into sodium ion, aqueous, and chloride ion, aqueous. A weak electrolyte, on the other hand, only partially dissociates into ions when we dissolve it. So if I had something like calcium carbonate, which we don't really think of as very soluble, it is chalk, right? If I put chalk in water, only a little tiny bit of the molecules will become calcium ions and carbonate ions. But more than not, it's going to stay as the calcium carbonate. You're only going to get a tiny little bit of the products. So that's what a weak electrolyte is. And then a non-electrolyte does not dissociate into ions when it dissolves, so there's no ionic interactions at all. And so here's an example of pure water. It is just a molecule, and so there's no ions in it. If I take something like sucrose, that is a molecular compound dissolved in water, so that one's going to be a non-electrolyte. And if I take sodium chloride, which is salt, right, it's going to completely break apart. It's a strong electrolyte, so the light bulb turns on bright. And electrolyte basically means that a substance will conduct electricity when it is dissolved. If we had a third picture here for a weak electrolyte, you would see something between sucrose and sodium chloride, where it would just be kind of a dim light bulb, indicating that only a little bit of ions are present. So now we're going to talk a little bit more about the quantitative value of concentration, not just being strong or weak or dilute or concentrated, but how do I actually quantify my concentration? This is important because the amount of solute in a solution determines a lot of the properties, which we're going to focus on in chapter 13. We call the amount of substance dissolved is concentration. And one of the units of concentration, the most, I don't want to say popular, but mostly used, is molarity. Molarity is defined as capital M, not to be confused with molar mass, and it's equal to the moles of the solute of interest in this case divided by the volume of solution. And so what we get is the units being mole per liter. So oftentimes people will talk about a solution being like 0.1 molar. That's the exact same thing as saying I have 0.1 moles per liter of solution. So you see there's a combo unit here. I have one on top and bottom. This should be kind of familiar. This is like when I say I have, 12 inches per foot. It's dimensional analysis. You could actually use it as a conversion factor between moles and liters if you have a solution. So in order to create a solution, when we want to, I'm creating a certain solution with a concentration that I want, I'm going to weigh out the known amount of mass, right? Because that is how we measure moles in a lab. We don't have a scale to measure moles, and so we measure out the mass and can convert to moles of the solute. Then you add the solute to a volumetric flask. That's what this glassware piece is. It's a very precise, you can't really see it well here, it's a very precise volume instrument where it has like a line indicated on the glass that tells you exactly what the volume is. So this looks like a 100 milliliter volumetric flask. Let's see. Nope, it's 250 milliliters. And so when you've gotten the line at the bottom of the meniscus, you have exactly 250 milliliters in there. So you're going to, weigh out your sample, the right mass that you want. You're going to put it into the volumetric flask. You're then actually going to put about a little bit of water in it, shake it up to dissolve the water, and then you'll top it up to the bottom of the meniscus. Whatever your solvent is. It could be water, it could be something else, depending on, what you're using. And once we create a certain solution, we can actually dilute it. This happens by adding only solvent. So this means that the concentration lowers, right, because I added more volume, but the amount of moles that were in my sample don't change. So if I pull out, looks like I'm pulling out, this is probably a 25 milliliters of my original solution. The amount of moles of that solution that I'm putting into this flask are going to stay the same. But now I'm going to dilute it with more of my solvent, and so the moles that were originally in this flask are going to maintain the same. I didn't, have a chemical reaction or anything. But now I'm going to add more solvent. And if we know that molarity is moles per liter, if I add more volume gets bigger, that means that molarity decreases. So this is a way to get a concentrated solution more dilute. You can't actually go backwards without evaporation, and it's harder to become more precise. The equation you're going to use only when you dilute a solution is the molarity of the concentrated solution times the volume of the concentrated solution, right? So whatever the concentration is here's my concentrated solution, here's the volume of the concentrated solution I took, is going to be equal to the molarity of my dilute solution, which is now this one, times the volume of how much I diluted it to. So in this case over here, I have a 1 molar solution of my concentrated, so I'd have 1 molar, times by, I took out 25 milliliters of it, and the nice thing is you actually do get to keep it in milliliters here. As long as your units of volume on one side are the same as on the other, it doesn't matter what they are. You could use another, like you use like cups technically if you wanted to. And then we're going to solve for what my diluted solution concentration will be, and then times by the volume of my new, I'm making of my solution, which is 250 milliliters. Solve for my diluted, so we would divide by 250 milliliters. And say, okay, my diluted concentration is 1 times 25 divided by 250, it's 0.1 molar.